Good afternoon, everyone. So welcome to the sixth colloquium on the SNBOS colloquium series on quantum materials and devices. And I'll request our director, Professor Tanushree Saha Dasgupta, to introduce the speaker. Please.
Okay, good afternoon, everyone. It's actually a great pleasure and honor to introduce Professor Hidenori Takagi. And of course, I know him for my association with MPI Stuttgart. So currently, Professor Takagi is director and scientific member of Max-Planck Institute for Solid-State Research in Stuttgart and also a professor of physics at the University of Tokyo. He studied applied physics and he received his PhD from University of Tokyo. And after that, he moved to Bell Labs as postdoctoral member. And then he returned back to University of Tokyo as an associate professor. And in between, he joined RIKEN and became as a chief scientist and group director. And he became director of Max Planck Institute for Solid-State Research in Stuttgart in the year 2013. The same year, he was also appointed the Alexander von Humboldt Professor, and he has received many prizes, which includes the IBM Science Prize, K.H. Holmes Prize, Honda Frontier Award, and he is also fellow of the American Physical Society. His research interest primarily is in the area of strongly correlated electron system, metal insulator transition. He was known for his work on this electron-doped cuprate superconductivity, and in recent time on quantum magnetism, in which his talk will be focused, where in addition to strong correlation, also the spin-orbit coupling plays a very important role. And it's really a great pleasure to welcome Haide on our seminar series. And I do hope that next time we will be able to visit Kolkata and we will be able to meet each other in Kolkata personally, face to face. So with that, I welcome you once again. And now the floor is yours.
Okay. So, Tanushree, thank you very much. And it's great, pleasure for me to see, old and a new Indian friend, there. And I hope I can travel to India, this fall, if, situation allows. Okay, so I'm delivering this lecture from Stuttgart, Germany. It is, ton of automobile industry, a lot of industry, around. And, this is a picture of our Max Planck, Institute, actually my office. Okay. So taking this opportunity, I would like to give a kind of colloquium on quantum spin liquid, which is, one of the major topics, at the moment. And today, let me start to, by introducing quantum spin liquid, in particular, development of concept from, RVV to Kitaev. And based on that, let me discuss the latest, progress of, Kitaev business. In particular, two compounds, hydrogen, honeycomb iridate, and ruthenium, chloride. So contribution from my own group has been done in collaboration with those people listed here. Yam Buin, Yosuke Matsumoto, and then Tomo Takayama, Kentaro Kitagawa. Those people has been a key player of this project. And here are kind of some reference. to this talk. Now, what is quantum spin leakage? And in a conventional, magnet, as you know, through interaction between magnetic moment, spins, you have, ferro, anti-ferro magnetic ordering, okay, which can be viewed as a broken symmetry below transition temperature Tc. And if you can measure entropy, magnetic entropy is rapidly quenched at the transition temperature Tc. But in the quantum spin liquid, somehow we don't see any magnetic transition down to T equals 0 limit. But of course, because of the thermodynamic law, entropy must go to 0. So therefore, entropy is quenched quite gradually to 0. And the ground state is somewhat quantum disordered, fluctuating quantum mechanically. And why quantum spin liquid is so interesting? First of all, we have strong quantum entanglement, and we have exotic quasi-particle excitations, in particular fractionalization of spin into spin-ons, Majorana fermions. And the people suspect quantum spin liquid state could be connected to superconductivity. And there is a possibility, spin pairs transform into Cooper pairs. And in some sense, we are, looking for state without, any long range, ordering. And this might be along the line of state of nothingness, central dogma of, Japanese Zen concept. So, according to, Zen, philosophy, okay, go to state of nothingness, like quantum spin liquid. And then you will see hidden reality, okay, which might be hidden fractionalized excitation, like, spin-ons, Majorana fermions. That's why, that this, topic of quantum spin liquid is kind of favorite of, Japanese. Okay. And this, concept of quantum spin liquid, history is quite, long. And the first, concept of quantum spin liquid was established in one-dimensional Heisenberg anti-ferromagnet. It was, kicked off even before Second World War, starting from, Bethe ansatz almost 100 years ago. And in 60, people, understood, elementary excitation of, a unique elementary excitation of 1D Heisenberg anti-ferromagnet. So people more or less know quantum spin liquid state there. Soon after, it was extended to higher dimension. In 1972, Phil Anderson proposed resonating valence bond state in 2D Heisenberg antiferromagnet on triangular lattice. And since then, this RVB type spin liquid has been at the heart of community of quantum magnetism for long. So we have been looking for quantum spin liquid in geometrically frustrated magnet, such as triangular lattice, Kagome pyroclo. And recently, new pathway has emerged. So based on the proposal of Kitaev. And my talk today is, kind of our effort to explore, Kitaev type, quantum, spin liquid. But before, getting into deep inside, Kitaev, physics, let me overview, this historical development. So first of all, the idea of quantum spin liquid, okay, early days, comes from instability of spin 1/2 anti-ferromagnet against quantum fluctuation. So let's consider okay, so this should be better. Yeah. So consider Heisenberg Hamiltonian. Okay, and if you have only G component in the Ising limit, this up down anti-fellow configuration is eigenstate. But once you have this SXXY component, okay, so this blue can be written as S plus S minus, some sort of a hopping of spin. And because of this this up down anti-fellow state is not real eigenstate of Hamiltonian. And this we can say anti-fellow state is kind of unstable against quantum fluctuation. For example, let's consider two spins coupled anti-ferromagnetically. Okay, and as two coupled spin split into S equals 0 singlet and S equal 1 triplet. Okay, and the energy of S equals 0 singlet is minus 3/4 J. And the anti-ferro state, up-down configuration is superposition of triplet and singlet. Therefore, only minus quarter J. So in the case of two spins, apparently, spin singlet state has kind of a lower energy than anti-ferromagnetic state. So this we call anti-ferro state is against quantum fluctuation. And so therefore people realized spin 1/2 anti-ferromagnet is not so stable against quantum fluctuation. In particular, when coordination number is kind of small. And in case of 1D, okay, so you have only two neighbors. So that means you have only n bond, right? So by forming an anti-ferro bond, so you gain only minus quarter Fj. And the spin singlet is formed by two spins, right? So therefore you have half n spin singlet bonds for 1D, or in any case, okay? And each bond gain minus 3/4 J. So therefore as a total, if you have array of singlet, the energy is minus 3s Nj, which is lower than anti-ferromagnetic state. So apparently, in case of 1D, anti-ferro state is unstable against the spin singlet state. In fact, this energy is close to correct ground state energy of minus 0.4 Nj. And of course, there are many ways of distributing spin pairs. And by kind of superposing different distribution, you can lower energy further. And this is somewhat experimentalist image of quantum spin liquid states. So you have different distribution of short range single bond, long range single bond, and you just quantum mechanically kind of superpose different distribution of singlet pairs. Right? So this state, of course, you can see quantum mechanically disordered. And in this state, you can have, quite exotic spin excitation. And consider one-dimensional chain in Ising limit. If you flip, this spin, okay, so you create a two-domain wall, and you immediately know in case of Ising, without costing any energy, you can move this spin domain wall, freely, and this domain wall, carries spin-off moment and acts as Fermi particle. Okay, and once you have this Sx Sy component, this acts as kind of hopping term, and using this term, those S equal 1/2 excitation, fractional excitation can hop around and can gain kinetic energy. And in case of XY, so you have somewhat the gas of free spin-ons, S1/2 excitations, and they form a Fermi surface. And because of the presence of Fermi surface like metal, so if you calculate the excitation, unlike magnon dispersion like phonons, you have continual excitation like metal. So that's kind of a signature of fractionalization of spins into spin-half Fermi particle spin-ons. And in case of Heisenberg, SG term acts as like interaction. So Heisenberg spin system is a kind of ensemble of interacting spin-ons. So those quantum spin liquid hosts sea of spin-ons. And in fact, experimentally, in a kind of neutron scattering measurement or X-ray resonance measurement, you can see continuum excitation coming from spin-ons kind of beautifully. And if you measure, say, like magnetic susceptibility, you see, Pauli like susceptibility, like metal, and the T linear specificity, like metal, and their Wilson ratio is close to 1. So although they are insulator, they behave like free electron Fermi liquid. So the physics of quantum spin liquid is kind of well established in 1D. And then, almost 50 years ago, Phil Anderson hit some idea, kind of similar quantum spin liquid state might be realized in higher dimension, in particular 2D, in between 3D and 1D. I think, as far as I understand, he was motivated by the observation of spin singlet dimer state in many of correlated electron system, such as vanadium dioxide, and he thought, spin singlet state could have lower energy than anti-ferromagnetic state, even in higher dimension. And in fact, using the same logic as 1D, okay. So you can show instability of anti-ferromagnetically ordered state. Okay, and suppose you have triangular arrays, and as you know quite well, once you fix this spin up and this spin down. Okay, so if you put down spin here, this bond is happy, but this bond is unhappy. And if you put up spin, this bond is happy, but this bond is unhappy. And as a result, with anti-ferro like order, you gain only 1/3 of anti-ferro energy. So although you have kind of 6 neighbors, at the end of the day, you gain only minus 2/8J. Okay, and singlet energy is always minus 3/8J. And as you see, this triangular lattice case, due to the deduction of energy gain for anti-ferromagnetic ordered state due to frustration. Singlet, state, could have, lower energy. That, what, Anderson claimed. And since then, many theorists, try to understand, what could be the ground, state of such state. And now we understand we can have, ground, quantum spin liquid as a ground, state. And we have, more than one kind of quantum spin liquid. So you can have, superposition of a different, singlet, pair distribution over space, like, 1D. And then you can have, distribution of only, short range, nearest neighbor, pair. In this case, you have, gapped, excitation. And then, like, 1D, you can have, distribution of short range, singlet and the long range, singlet, and, superpose. And in this case, because of, very long range, singlet, so you have, zero energy excitation, and the excitation is, gapless. So you have, more than one kind, a gapless, gapped. And in case of, triangular lattice, 2D, at the end of the day, it turned out if you have only nearest neighbor interaction, 120-degree ordering is kind of stable. So in order to have this kind of quantum spin liquid state, you need additional ingredient such as close proximity to metal to insulate a transition. But if you have Kagome lattice, okay, so you have only 4 neighbors, and that destabilizes anti-ferromagnetically ordered state a lot, and even only with your nearest neighbor interaction, you can have quantum spin liquid. But because we cannot solve Hamiltonian exactly, so we don't know yet what is the ground state exactly. And there is ongoing event. What is the ground state of Kagome quantum spin liquid? Some says it's kind of a gapless U1 quantum spin liquid. Some says gap G2 spin liquid. And hallmark of those 2D RV type quantum spin liquid is again fractionalization of spins into spin-ons. And again, this S equal 1 excitation split into 2 almost free spin 1/2 fermions called spin-ons, and they form Fermi C, Fermi surface, and so Fermi surface of charge neutral fermions. And if you could measure excitations, you are supposed to see again continuum excitation rather than well-defined line like Magnon excitation. So although they are insulator, they are supposed to behave like metal. And somehow many people visited this problem. And in the last 20-30 years, we experimentally discovered many candidate material for quantum spin liquid, including inorganics and organics. And many of compounds shown here, they don't show long-range magnetic ordering, so they do see nothingness. But of course, in order to establish quantum spin liquid, we have to capture the fractionalization of spins, spin-ons. Okay, but capturing such excitation is quite difficult, and the only those 2 compound we might have seen such fractionalization spin, but still debate is kind of ongoing. For example, this organic quantum spin liquid. Okay, this DMIT, so you have spin 1/2 molecule, forming a triangular lattice. Okay, so you don't see any magnetic ordering, down to 20 milli-K, nothingness. And you see, Pauli, like, magnetic susceptibility, and the linear specific heat, like a metal, and the Wilson ratio is, close to 1. On top of that, the group of, Matsuda, measured, thermal conductivity. And the thermal conductivity is, essentially scaled by specific heat. Okay, but what the difference is, C times, mean free path, right? So they do see T-linear contribution of thermal conductivity, but to see that, you need a sizable mean free path. And this observation, large, T-linear thermal conductivity means, we have, highly mobile excitation, and that has been, taken as, evidence for the formation of, spin-on, failing surface. But, I have to, for the sake of fairness, I have to mention, very recently, during, Corona, this reproducibility of this result was, questioned. And at the moment, debate is kind of still ongoing. And this, organic, Haber smithite, compound made of spin and half, copper. Okay, so they have been taken as the best, candidate for, Kagome anti-ferromagnet. And some time ago, people observed, continuous, spin excitation for this, compound, and this is kind of a signature of kind of flux rotation. Now, people try to identify whether there is any gap in excitation or gapless, but due to the presence of disorder, this identification of excitation gap is, still subject of hot debate, and we don't know, which one is, correct yet. So so far it's kind of a story about, RV quantum spin liquid. So as you see, even the RVB spin liquid is interesting. But, recently, Kitaev, brought, a fresh, wave to the community, and he proposed a new generation of a quantum spin liquid. And this type of, quantum spin liquid, physical image is kind of clear, and the excitation is, kind of better, kind of defined. So in that sense, even kind of more interesting for experimentalists. So Kitaev, proposed quite, simple, but, elegant, model. So he placed, spin and half spin on top of, honeycomb lattice, and, connected to, spin and half, moment, with, 320-degree bond. And each, bond, okay, has, Ising, ferromagnetic interaction. Okay, and the easy axis is kind of orthogonal to each other, and this, green, has, Ising axis of X, and the blue Y, and the red G, right? So therefore, this, bond, try to polarize spin to X direction, and this bond try to polarize spin to Y direction, and this bond try to polarize spin G direction. So they kind of conflict each other. Okay, and due to the conflict of three bond, quantum spin liquid state is kind of realized. You may, consider like maybe, ground, state, you have to kind of compromise, and you have, different distribution of ferromagnetic spin pair, and superpose those, like, RVB. But, unlike in RVB, we have, better idea what is the ground, state. Kitaev showed this, Kitaev Hamiltonian, on honeycomb lattice is exactly solvable. So what, he did was, he kind of fractionalized, okay, spins into two kind of, Majorana fermions. So he introduced the two Majorana operator for spin moment. spin operator. And one is, B, called localized, Majorana, representing ferromagnetic bond. And, C is, called itinerant, Majorana, placed, on top of, spin alpha moment in place. And, Hamiltonian, using, Majorana operator is like this, and C is, this, C operator. And U is, from, this, B operator, and the B operator give rise to a G2 flux. And in the ground state, G2 flux, should be uniform. And this value should be, plus minus I. Okay. So therefore, those are kind of a constant. And, you have only C parameter on top of honeycomb lattice, like tight binding Hamiltonian for graphene, right? So therefore, this, C Majorana has, Dirac dispersion, like, graphene. And ground state, you have, C of C Majorana fermions, okay, in the ground state, right? So we know what is ground state. And what is interesting is if you apply magnetic field creates, gap. Okay. Now, the system changes from, gapless to gapful and topologically protected. And associated with gap formation, the system is kind of protected topologically. And this, topological protection appear as an edge state of, Majorana fermion. And this, Majorana chiral edge state, of course, neutral in terms of charge, but of course, they can, carry heat, and they can be detected as, half integer quantum thermal Hall effect. So thermal version of, quantum Hall effect. Okay, and this, half quantization. Okay, half quantization. Okay. Represents, so you have two kinds of, Majorana fermions, and only C Majorana fermion carries this Dirac, degree of freedom. Okay, but anyway, so this case, we can capture, exotic quasar particle Majorana fermion, through edge state, thermal Hall conductivity. Now, so how to, make up, such, Kitaev quantum spin decay. And of course, essence of Kitaev model is, Ising, spin 1/2, but normally, pure spin 1/2, interaction is Heisenberg-like. Okay. And my, Stuttgart colleague, Jacqueline and Caroline, they kind of proposed, okay, to make, Ising board, use, spin orbit coupled J1 moment instead of spin 1/2. So they proposed, like a place, D5 transition metal element inside, octahedral cage, like iridium 4 plus, ruthenium 3 plus. Then you have D5, situation, and L equal 1, and spin 1/2, and following, LS, coupling scheme, L minus S equal 1/2. So they behave like a spin 1/2 moment. However, because they have large orbital moment, LG equal 1. Okay, so you cannot flip orbital moment like spin off, and therefore they behave like Ising moment. Okay, also 1/2. And because regular exchange hopping between J1/2 state is kind of forbidden due to interference between two oxygen between kind of octahedron. So like so if you put two octahedron kind of together by sharing edge due to this oxygen direct hopping prohibited. And the only way is hop to higher J3 half state. And due to Hund's coupling, this gives rise to ferromagnetic coupling. Right? So because of that, between two neighboring J half site with edge shared bond over two octahedron, you can have ferromagnetic edging interaction, which is nothing but the essential ingredient of Kitaev model. Now, so if you consider octahedron, you have three orthogonal edges, right? So if you use three orthogonal edges, so you have three Ising bond, and since those bonding plane is kind of orthogonal to each other, so Ising axis kind of orthogonal to each other, x, y, z. Okay, so that's again essential ingredient of Kitaev model, and now using this 120-degree bond, you just connect those 120 bond and make up honeycomb lattice, right? So this honeycomb lattice, if only near neighbor interaction kind of dominant, you are supposed to have Kitaev model. And fortunately, there are many iridium 4 plus or lutetium 3 plus compound. What happened?
Can you please mute? Please mute.
Oh, okay. Okay. Now, because of that, there are many kind of compound with iridium 4 plus, lutetium 3 plus, having handicap network of iridium 06 and lutetium chloride octahedron, like lithium 2 iridium 03, sodium 2 iridium 03, or lutetium trichloride. This is nothing but materialization of a Kitaev model, and many groups, including us, rushed into those compound with the expectation of a quantum spin liquid state. But unfortunately, as you see from specific heat data, okay, there is quite clear signature of low temperature phase transition. This is magnetic ordering, and all candidates proposed early days showed long range magnetic ordering, either zigzag or spiral. Unfortunately, so ground state is not Kitaev quantum spin liquid, but long range ordered state. So 10 years ago, the community wasn't too happy about this. But since then, somehow we got some progress towards Kitaev quantum spin liquid, and using remaining 10-15 minutes, let me go through quite recent progress along this direction towards Kitaev quantum spin liquid. And there are kind of two compound emerged in the last 5 6 years. One is hydrogen iridate, and the other is ruthenium chloride. And in this hydrogen lithium iridate, okay, with honeycomb network of iridium 06 octahedron. Okay, we kind of discovered, okay, by replacing interlayer lithium ion of lithium to iridium 03 within hydrogen. So it's kind of isovalent. Okay, only the changes, interlayer ion is kind of exchange to hydrogen, but somehow this exchange, okay, modified magnetic property of compound a lot, and this is lithium and hydrogen kind of NMO, and down to less than 1K, you don't see any kind of split or broadening of NMO peak, signature of magnetic ordering. And in susceptibility, again, you don't see kind of anything. So we do see kind of nothingness. And the ground state appear to be a quantum spin liquid of J1 half moment. Now we can expect, Kitaev quantum spin liquid. And of course, we aim to explore, possible signature of Majorana fermions. But unfortunately, our kind of a recent, effort, reviewed, okay, this, system, might not be an ideal playground to hunt, Kitaev physics. For example, taking a look at, specific heat, okay, at low temperature, you see T cubed specific heat, coming from, phonon. And unfortunately, at, low temperature, below 10K, we don't see any signature of a magnetic contribution. We seem to have, some sort of excitation gap in this, compound. And we did, isotope experiment, replacing a hydrogen with deuteron. And we discovered giant isotope effect in the sense, Curie-wise, temperature is, doubled from hydrogen to deuteron, meaning, energy scale of magnetic interaction, changes, by factor of 2. But nevertheless, magnetic interaction changed a lot. We still see quantum spin liquid state. So quantum spin liquid state, seems to be quite, robust against the change of magnetic interaction. But such, robustness is not, expected for pure Kitaev. And perhaps, some other ingredient, must be working, here, likely related to deuteron and the hydrogen. So in that sense, quantum spin liquid, state of this compound is extremely interesting, but perhaps, a bit, away from Kitaev physics. And in parallel with that, new star compound showed up, ruthenium chloride. Okay. Again, they have, network, honeycomb network of, ruthenium, chloride, octahedron, edge, shared, mimicking Kitaev, model. And in zero field, they show zigzag anti-ferromagnetic ordering below 7K. So under zero field, the system is anti-ferromagnetic, not, quantum spin liquid. But somehow people found if you apply magnetic field parallel to the honeycomb, plane, somehow this, 7K ordering is suppressed, and eventually goes away. And you see some sort of paramagnetic state above, 7 Tesla. Now, many people believe, this, paramagnetic state is, magnetic field induced quantum spin liquid state. And in fact, this, high field, paramagnetic state, people discussed many signature of exotic quasar particle. So first of all, in a neutron inelastic, scattering, the group of Oak Ridge, they found, continuum-like, excitation, okay, like, this, and, claimed, okay, it is kind of a signature of spin fractionalization. And perhaps, even more importantly, the group of Yuji Matsuda from Kyoto, they measured, thermal Hall effect. Remember, chiral edge, Majorana chiral edge state, should, give rise to quantized thermal Hall effect. And they discovered, thermal Hall conductivity close to quantization value in this, field-induced, paramagnetic quantum spin liquid region. That was shocking. But still, their result is kind of a, subject of big, debate. For example, if you take a look at, data, Okay, as a function of field, there seems to be some sort of plateau state. As a function of temperature, okay, so this is the expansion of this part, and maybe you may draw a line like this, at quantized value, or you may draw a line like this, and the temperature plateau is not clear at all. And later, group of Fan Ong, from Princeton, they measured some thermal Hall effect, and they say no half integer plateau, only broad peak, and magnitude it's half to 1/3 of quantization value. But instead, they find something exotic. So they measured longitudinal thermal conductivity, kappa XX, and they find quite oscillatory structure, and they assigned this to quantum oscillation, like metal, of neutral quasi particle with small kind of Fermi surface. So something exotic must be happening, but we don't know what it is. So as a kind of since we worked on this hydrogen iridate, we at the beginning we didn't come to this ruthenium chloride business, but somehow I couldn't stop my young colleague to start working on ruthenium chloride, and they wanted to explore something like this. Yeah, because of kind of debate, they wanted to examine half quantization of Hall effect independently. Maybe we can extend temperature and the magnetic field range of measurement, in particular down to low temperature. And can we see similar oscillatory structure in thermal conductivity? And what is the origin? And fortunately, we got the same source of crystal as Kyoto Matsuda group called the Bridgman crystal. And also we have so-called CVT crystal, somewhat similar to Princeton group used. So we have two different source of crystal to examine those issues. And the picture of a crystal is kind of like this. And let me kind of rush. Okay. So first of all, just longitudinal thermal conductivity. We reproduced Kyoto result quite well, and we used the kind of same crystal as Kyoto group. And as a function of field, okay, this red, thermal conductivity shows complex structure like Princeton group observed. Okay. But taking a look at the detail, okay, so this black curve is magnetization, derivative of magnetization. And here is kind of sharp structure, Hc1, Hc2. This is nothing but magnetic phase transition associated with collapse of zigzag magnetic ordering by in-plane field. Okay, so at least two kind of a bottom of a kappa XX deep correspond to two kind of phase transition. And when you have magnetic phase transition, you have soft magnetic excitation. And we believe kappa XX is dominated by phonon thermal transport. And if you have a lot of soft magnetic excitation due to scattering of phonons by soft magnetic excitation, you have suppression of kappa XX thermal conductivity. So we believe those deep correspond to soft magnetic excitation at magnetic phase transition. And we see additional dips here and there, named H2, H3, H4, H5. And then naturally, we consider those additional complex features represent high field phase transition crossover. But of course, we know Princeton group is saying they originate from quantum oscillation. And let me, tell you, some experimental evidence, they are coming from high field, phase transitions, not, quantum oscillations. Okay. First of all, okay, so this is kind of comparison of Princeton result and our result and the CVT result. And we see kind of a dip, okay, at the same, field. So therefore, we are seeing the same, phenomena. Okay. And this is a Bridgman crystal, okay, we used, okay, has, higher thermal conductivity, okay, less disordered. But we see smaller oscillatory structure. And this is kind of opposite to what is expected for quantum oscillation. Quantum oscillation, cleaner crystal, you see bigger oscillation. On top of that, okay, if you trace, this oscillatory structure for Bridgman crystal and the CVT crystal, okay, so this is the oscillatory part. And this, magnitude oscillation, once, increases with decreasing temperature, but below 1K, they start, decreasing. Well, this is, magnitude of a kind of oscillation, okay, as a function of temperature. And above, 1K, you see increase, like, quantum oscillation, Lipschitz, Kosevic behavior. But below 1K, suddenly magnitude, goes down. This is not, expected for, conventional, quantum oscillation. And besides, those, peak portion, as you see, temperature dependent. And you can see temperature depends like this. Okay. And for the collapse of zigzag ordering, called HC1, HC2, people observed tilting of a phase boundary due to entropy effect. And somehow you do see quite a similar behavior of those peaks, and they behave like thermodynamic phase boundary dominated by entropy effect. So this really look like phase boundary. And besides it is known in addition to 7.5K transition for the non ruthenium chloride crystal, you have some secondary phase called the 10K 13K phase, which people discuss produced by stacking Hall. So the major phase is always 7K, but you have tiny secondary phase likely produced by stacking for 10K 13K. And we carefully checked how those minor phase transition behaves under magnetic field, and we found that those 10K 13K phase transition is smoothly connected to the deep position we observed in thermal conductivity. And that is kind of a definite evidence, at least this anomaly at H4 and H5 comes from magnetic phase transition. And the 11 Tesla transition, we don't see a clear-cut connection to high temperature phase transition. But a group of Yuji Matsuda, they are saying this is related to topological phase transition to ordinary state, and therefore represent disappearance of quantum thermal Hall effect. But we want to say this 11 Tesla transition, they are also behave like phase transition here. Okay. So okay, from this we conclude that it's magnetic phase transition. And finally, let me show you thermal Hall effect result. And this is the result of thermal Hall effect measurement as a function of field and different temperature. And you can see around 5K, 5.6K. Okay, so this is quantized value, and you see a large thermal Hall effect above 7 Tesla, and around 5K, 6K, there seems to be some sort of plateau state, but unfortunately, with lowering temperature further, at least up to 10K, thermal Hall effect goes down and go to 0. Okay, so in that sense, somehow there is no temperature plateau below 10 Tesla, but somehow above 10 Tesla, the suppression of thermal Hall effect is kind of suppressed and quite gradual, and there seems to be a substantial thermal Hall effect left down to low temperature above 10 Tesla, close to a half quantized value. So to trace that, we checked, temperature dependence of Hall effect at a fixed field. And as I said, below 10 Tesla, okay. So thermal Hall effect, goes down, and nothing special, at half quantization value. So at low field, we don't see any signature of temperature plateau. But above 10 Tesla, somehow you see some kink-like structure around half quantized value, and at high field, you start seeing some sort of plateau-like behavior, okay, down to low temperature. This observation can be summarized in this color plot, and white region represent thermal Hall effect close to half quantization value, plus minus 15%. And as you see, it's just line, but at the high field, you see some plateau-like state spread over finite temperature and field window. And we see kink-like structure at half quantization value. Of course, our resolution is plus minus 50%. So therefore, it might be fair to say within our resolution, plus minus 15%, consistent with Majorana edge state scenario. But within this, so this is not like electric quantum Hall effect. So we have huge error bar, and within the solution, we cannot completely rule out Magnon scenario, phonon scenario, rather than Majorana fermion scenario. But of course, those scenario must explain the significance of half quantization value. Okay, so I think that's all, and this is kind of my summary. So in the last 5 years, we got big progress in our Kitaev quantum spin liquid business, and we find zero field quantum spin liquid in hydrogen iridate. And we are sure about quantum spin liquid state, but lacking is the Kitaev signature, in particular Majorana signature. And in ruthenium chloride, so we need a magnetic field to induce quantum spin liquid. But instead, we see quite interesting and exotic features there. And as we show in the last view graph, thermal Hall effect equal to half quantization value seems to have significance. So we see kink and some finite plateau region on the BT plane, okay, within plus minus 15%. And the Lodgian component shows complex structure as Princeton group observed above critical field, but we show explain evidence they originate magnetic phase transitions rather than quantum oscillations. So that's kind of two important message today from me. And by saying so, thank you very much for your attention. Thank you.
Yeah, thank you, Professor Takagi, for giving us such a nice and exciting and informative overview of quantum spin liquids. So now the floor is open for questions. So please raise your hands to ask your question. So I just see first question from Nashra Pishtawala. So Nashra, you can ask your question. You unmute yourself and ask your question.
Sir, I'm audible?
Yes, yes.
Okay.
Yeah, I can
So
hear
I have a very fundamental question.
Yes.
That why application of magnetic field, like in fact, how application of magnetic field alters the spin orientation, leading to a disordered quantum spin liquid state in RuCl3.
Very good, question. And actually, there is a kind of theoretical discussion, but somehow, this, all the other state kind of, kind of zigzag, and there is, quite, complex interaction due to anisotropic interaction. And the magnetic field is quite uniform, right? Try to align, spins for one direction, right?
Yes.
But underlying, interaction is like X, Y, Z. They try to orient spins kind of a different direction, right? So therefore, somehow, they kind of conflict with magnetically ordered state, and perhaps, marginally stabilize, quantum spin liquid, state. That's kind of my understanding. Yeah, but of course, this is kind of field in this state. And above critical field, we see magnetic moment of 0.6 mu b.
Yes.
Okay, so that means we have quite aligned moment along field direction already in the so-called spin liquid state, right? So in that sense, the situation is not exactly what Kitaev kind of handle. That's also true.
Yes. Yes. Thanks a lot, sir.
Yeah. So the next question is from KB Yogendra. KB Yogendra, can you ask a question now?
So can you hear me? So,
Yes.
so the are these phase transitions appear in magnetization plots also, like in the magnetization?
Sorry, say it again.
Are these phase transitions appear in magnetization? Like the magnetization show these kind of phase transitions here, like HC1.
I mean, are you asking magnetization data?
Yeah.
Magnetization as a function of field, or magnetization as a function of
Field as a function of field.
Okay, so actually, yeah, this black curve is the okay. This is kind of derivative of n. Okay, so in general, like with application of magnetic field, okay, magnetization kind of goes up monotonically, okay, towards saturation. Okay, but there is kind of a structure in the increase of magnetization. So okay, this derivative represents those kind of structure kind of beta. You see this? Yeah. So okay, there's actually the slope of magnetization is quite steep. So it's like a kind of almost kind of jump. Okay. So that's what you see in magnetization.
Okay. Thank you.
Yeah. The next question is from Sanjay. Please ask your question.
Yeah. Thank you, Chair, for your. Am I audible?
Yes.
Yeah. Yes. Thank you, sir, for nice talk. So I have question on H3Li IR206. So on your last slide, you mentioned lacking Kitaev signature, but H3Li IR206, this hexagonal and bond-dependent interaction. So that's how it is Kitaev. So there is no geometrical frustration. So what kind of, but it's also established QSL. So what kind of QSL it is? can we call Kitaev QSL, or again you are saying Kitaev lacking Kitaev signature? So which category QSL we can talk about this compound?
The question is, what is source of frustration in a Kitaev magnet? Is that in the question?
No, my question is, so H3Li R2O6, here the frustration coming from bond-dependent interaction hexagonal. So hexagonal, there is no geometrical frustration.
Yeah.
So,
that's correct. Yeah. So you are saying a honeycomb, right? The honeycomb is bipartite. So therefore, if it is a boring antiferromagnet, it's boring.
So this way it is going to the Kitaev direction. And again, it's established QSL through the experimental measurements, but it's lacking the Kitaev signature. So now can we say that it is Kitaev QSL, or what is which category QSL we can talk about this compound? And you said that due to some hydrogen, it's converted to QSL.
I see.
Yeah. Can you please?
Yeah. So that part, yeah. Yes. Mm-hmm. Yeah. Okay. Now I understand that. Okay. Sorry. I was slow in understanding what you were saying. Yeah. Yes. So I think okay. So this actually originally we claimed that Kitaev magnet, but in reality the major interaction appears to be anti-ferromagnet, and we don't know exactly what is anisotropy of interaction. Okay, so even anti-ferromagnetic case, if interaction is anisotropic, you can have frustration, and Kitaev like quantum spin leakage. Okay, so like as you said, if it is Heisenberg and anti-ferromagnetic, since honeycomb lattice bipartite, you do expect boring anti-ferromagnetic. But of course, experimentally, we are sure the ground state is quantum spin leakage. So something must be happening. And of course, there could be kind of many reasons. Okay, it's kind of quite speculative. But of course, there could be some sort of anisotropy. Bond-dependent anisotropy is still kind of working here, although it is anti-ferromagnetic. In terms of honeycomb anti-ferromagnet, if you have second neighbor exchange large enough, you can have quantum spin leakage. Number three, if you have those hydrogen deuteron may have done kind of something as you said at the end.
Some disorder is creating.
And at the moment, since we know actually this position of hydrogen and deuteron, there is okay. So let's see. So hydrogen and deuteron is located in between kind of oxygen. Okay, yes, but there are kind of two sites for hydrogen and deuteron.
Yes.
Okay, so they form a kind of a double wave potential. And if they distribute randomly for the two sides, okay, and then they give rise to strong disorder. But there is a possibility of some sort of a quantum motion of hydrogen and deuteron. And the optics guys suggest that they are kind of quantum mechanical, quantum tunneling takes place.
Okay.
But anyway, like a disorder or quantum tunneling, they might play a role. And that's kind of interesting question, but we don't know the answer yet.
Yeah, sir, I have one more question.
Yes.
Sir, I have read on your paper somewhere mentioned there is some iridium 5+ might come into picture in this H3Li IR206 due to some hydrogen is random. It's not the exactly positioned. So hydrogen is randomly moving. It's not like other atom AG or other. It's not perfectly 180-degree dumbbell. So some iridium 5+ possibility is there. So I could see the NMR, it's on 10 in paper. On paper also it's mentioned a spectra up to on 0 Kelvin. So above, have you noticed some another small peak or something? I couldn't find in your literature. No, means there 300K spectra. Just I want to ask you, what about the 300K spectra?
That's
is there anything?
Yeah, that's I'm sorry, I'm not an NMR person, so I have to ask my colleague Kentaro Kitagawa.
Yeah,
As
please.
far as I understand, they didn't find any kind of particular peak,
Yeah, no. The iridium 5+, some percentage of iridium 5+ might be there. So it's mentioned on.
Okay, but
so whether
yeah. So I think
so iridium 5+ is some non-magnetic things. Okay.
Yeah,
so
I know what you mean. Yeah, D4 is non-magnetic, right? Yeah, but we did rigs, and if we have a substantial amount of iridium fibrous, we know what it is. Okay, but those rigs spectrum, you see a kind of spectrum specific to J1 D5.
Okay.
That's you can find I think in a kind of supplementary of our paper.
No, 300K is not mentioned. 300K NMR spectra I'm talking about. It's not mentioned anywhere.
But I think in a supplementary, I think we put this RIX data, and I think RIX data is at room temperature.
Maybe Sanjay, I think you should write him an email, and he can address your maybe queries.
Okay, sorry, actually,
yeah.
But
thank you.
I understand your point. Yeah. But I don't think it is iridium 5+, and maybe I can show you the detail. Yeah.
Okay, sir. Thank you, sir. Yeah.
So, Nashra, I see your hands raised again. You can ask your question.
Yes, sir. Again, I have a very small question. Like, since this Kitaev materials interaction is a bond-dependent interaction, so how the length of the bond will affect the Kitaev interaction? Like, is there any studies or something like this?
Yes, actually, yeah. So you can find many kind of theoretical paper, in particular, based on boundary calculation, and it's quite sensitive to bond. The reason the following. So can you see the screen?
Yes, sir, I can see it.
Yeah. First of all, okay. So this ferromagnetic interaction comes from this 50-degree bond, okay, and also cancellation of two paths. There is a two iridium oxygen iridium path, and they interfere and cancel out. That's quite important. But if there is kind of any kind of asymmetry, cancellation is imperfect. Okay, and also and also like there is direct DD overlap. Okay,
Yes.
between this and this configuration of bond kind of modified direct DD interaction. So it's quite sensitive. But that's why we try to modify kind of a lattice, like by replacing lithium with hydrogen.
Yes.
So they must be quite sensitive to alkaline ion, and they should be quite sensitive to kind of pressure.
Thank you, sir.
Good point. Yeah.
So one small question, very basic question. Like we always, when we talk about quantum spin liquids, we say that there is no ordering down to lowest measured temperature and there is long-range entanglement.
Yeah.
So are there any experiments through which we can verify that in a material there is a long-range entanglement?
Very good question. And actually, so observation of long-range entanglement is
Yes.
of course definite answer. Okay, quantum spin liquid exists, and from experimental side, say like if there is a long-range entanglement, that should show up noise. Because you can measure kind of a noise, from spin, and it kind of reflects, whether we have kind of long-range entanglement or not. And I see some people are trying to make some effort to detect, something like that.
Okay.
Yeah. Of course, you might consider something like put the local kind of spin detector and see kind of entanglement. But I think although some people are saying quantum computing using a quantum spin ticket, but we are away, very far away, from actual quantum computing. But of course, viewpoint of entanglement is quite interesting, and that's why some people are interested in measuring noise.
Measuring in the noise in what signal, sir? Like
As a function of kind of a frequency, so you can see like a spin noise.
okay.
And of course, the spin noise includes kind of correlation, right? And there, you must be able to find the long-range entanglement.
Okay.
I think I think there is a few papers already kind of published along that direction.
Okay,
Yeah.
so I see C
Thanks a
Dhanashekhara
lot,
also.
sir. Thanks a lot, sir.
Yeah, thank you, Nasha. So C Dhanashekhar, can you ask your question?
Hello, sir, I'm audible?
Yes, yes.
Yes, thank you for the presentation, sir. I have the question which I wrote in the chat box. All this material shows the Kitaev spin liquid features at low temperature. Generally, we need application at high temperature, right? Room temperature, this kind of features at room temperature. So is there any material can we see at room temperature, this kind of features?
Yeah, of course.
That's what,
Yeah. Very good question. But I think it's kind of related to energy scale of magnetic interaction. And normally, like super exchange, like 180-degree, d electron oxygen 2p, interaction, can be say like 600, 700. So even at room temperature, J is kind of bigger than room temperature, and you see some physics. But unfortunately, if we rely on this kind of higher order process, like using a 90-degree bond, this energy scale is kind of limited to 100K, 200 K. So in that sense, within this octahedral cage kind of a connection, it might be difficult to reach kind of room temperature. Perhaps we may need other mechanism to realize Ising interaction.
Okay, thank you, sir. Sir, I have another question.
Yeah. Yes.
Generally, in the papers, it is mentioned that the ferromagnetic Kitaev and antiferromagnetic Kitaev states.
Yeah.
How to understand this from the experimental point of view? Generally, we do the 1/K versus temperature, and we can see the positive and negative intercept, where we can see that antiferro. Is it the same way to understand these two things?
Yeah, because yeah, maybe if you consider this Kitaev business as conflict of three bonds, right? And so this conflict of easy axis is a kind of a source, right? So in that sense, it doesn't depend on whether this spin pair is ferro or antiferro.
Okay.
You see?
Yes,
So,
sir. Okay.
yeah, like this try to make like a x pair, y pair, g pair. Okay, so that's the source, and whether x pair is kind of anti-ferro or ferro, it doesn't matter. I think
Okay.
so it's kind of symmetric. However, I understand from my kind of theory colleagues, stability of quantum spin. So like if you have pure architecture model, okay, it doesn't depend on sign of k, plus minus the same quantum spin liquid, same Rana physics. But once you have other interaction involved, story would be different. And okay, other interaction try to kill Kitaev quantum spin liquid. And as far as I understand, ferromagnetic Kitaev is kind of more kind of stable against the external perturbation. Addition of other type of interaction, and the anti-ferro Kitaev is extremely unstable. With minute of perturbation, quantum spin liquid immediately goes away. That's my understanding. But that's why I say the robustness of quantum spin liquid state, okay, against the change of a magnetic interaction is against, okay, Kitaev scenario for the quantum spin liquid state of hydrogen iridate.
Okay, thank you, sir. Sir, I have another question.
Yeah.
Sir, how the superconductivity and this QSL state related? Is there any like something? Can we think in that?
That of course, as a kind of a material physicist, we are interested in that direction as well. Particularly, some of my colleagues, and in general, let's see. Yeah. So I think it's theory colleague. Okay, so they are quite romantic, and they say anyway. So those quantum spin liquid in general is a kind of super position of kind of spin pairs, and those spin pair could transform into kind of a Cooper pair. So in general, there should be connection between quantum spin liquid superconductivity. And the same is true for Kitaev quantum spin liquid. But of course, as you see from this statement, in case of Kitaev, you might expect quite exotic Cooper pairing. Okay, so in that sense, theoretically, it's quite interesting. But in reality, it's quite hard to make those Kitaev candidates metallic, and some of candidates become metallic, but no superconductivity found yet.
Okay, thank you, sir. Thank you very much.
I see one question from this chat box. So he asks that recently there are some reports of stabilization of quantum spin liquid state on spin half triple perovskite, that is barium copper antimony oxide, and S equal to 1 triple perovskite barium nickel antimony oxide, where the magnetic part of the specific shows T square dependence in addition to linear T dependence expected as the signature of QSL. Would you like to comment on the T square dependence? Should it also be considered as a possible signature? Such behavior was also seen for nickel gallium sulfide. So I don't know whether this question you understood what I just.
No, I understand that. I understand that.
Okay.
Yeah. So yeah. So yeah, this barium copper antimony, I think that's actually work from my colleague Nakatsuji, right? And but they say some sort of random singlet state at the end of the day. Okay. So in that sense, disorder plays quite important role, there. And in general, many of those quantum spin liquid, we see T square temperature dependence of specific heat. And there are kind of many kind of a scenario kind of proposed, for that. But including, this T square, comes from, some sort of random, singlet, pairs. Okay. And in fact, many of quantum spin liquid candidate, we don't see quite a clear signature of mobile quasi particle. Namely, thermal conductivity go to 0, kappa over T go to 0, and so those quantum spin liquid state, quasi particles seem to be quite localized. And in that sense, those random singlet, scenario might, better fit to, many of those, quantum spin liquid, candidate. And I personally suspect that these T-scale might, capture, that kind of, random singlet distribution. But, I don't have, concrete, evidence for that.
So yeah, I have I don't see any other raised hand, so I'll just ask my. So you were showing this quantum oscillation data, and there's a controversy. So this quantum oscillation should be periodic in 1 by field, no? So is it periodic in 1 by field, and it's very big coincidence that it is a magnetic transition, but still periodic in 1 by magnetic field.
Yeah. So okay. First of all, as I said, I do not, believe this quantum oscillation scenario.
Yeah.
Okay. And although I respect Van Ongen a lot, but this specific claim, I don't believe. And according to their paper, they say, this location of, deep, peak.
Yes.
Okay. And they put kind of a linear line, and the slope, changes above and below.
Yes.
And but as far as I understand, they see only 2, or at the most 3 peak above and below.
Yeah.
Okay.
But the amplitude.
So in that sense,
Yeah, as you also showed that amplitude becoming smaller as you went to lower temperatures is quite a clear signature also.
Yeah, and I think they plot, they plot, peak position and deep position as well.
Okay.
So it seems like you have kind of many peak point, but in reality they put both peak and deep. Yeah. So therefore, they have only 2 or 3 peaks, and I think, I'm not kind of convinced, kind of linear dependence, only from 2 or 3 peaks.
Yeah, definitely. So I have my last question. So the question is whether you had finished your lunch before you started this talk. So because it is stretched for so long. So had you finished your lunch before you started this colloquium? So because it stretched for a long time. So I hope that you had finished your lunch before you started the colloquium.
Have I finished what?
Your lunch. So it was just I was.
Lunch.
Yeah, because it is quite late now.
Don't worry.
Yeah, because this timing is 12:30 for you. It is exactly the lunch time. So we are very sorry about it.
That's fine.
Yeah. So I don't see any other raised hands. So let's thank the speaker, Professor Takagi, again for his nice and excellent and informative talk. So thank you, Professor Takagi.
Okay, thank you very much. And yeah, maybe sincerely, I could have said hello to you.
Yeah, but you should tell her hello once you physically come here. we'll invite
Okay.
you for that.
Okay. Okay.
sure.
Okay. Thank you very much for kind words.
Thank you, Professor.
Yeah.
See,